Hello, everyone. In today's lecture, if you remember, we are done with the particle equilibrium. We did the particle equilibrium in 2D and then in 3D, and that's pretty much it in statics. The next step is to start looking at bodies that cannot be considered as particles. And if they are not considered as particles, it means that the forces are not concurrent. The forces acting on this body don't meet at a single point, so they are capable of producing rotation. So now it's not enough for us to apply Newton's law and say, oh, the sum of the forces in all directions equals zero, so the body is in equilibrium. No, the body may be rotating, changing direction, hence it will have an angular acceleration. So now we need to add more constraints on the body to prevent it from rotating. But in order to do that, we have to talk about what we call torque or moment. And in order to do that, we need to start looking at another type of vector multiplications. Remember, we said we have two ways of multiplying two vectors. One of them is called the dot product or the scalar product, and we use that to project vectors in many directions. And it's basically when we say f cosine or f sine that we are doing, without realizing, we are doing dot product of vectors. But then, in order to consider the rotation, we have to start learning about how to multiply two vectors in cross product or vector product of vectors. And that's what we are going to do today. We will be referring to something called the determinant of a matrix that we haven't covered so far, but I plan on my other channel for Math Made Easy to start discussing matrices and determinants in more detail in the next few videos. Okay, so today I'm going to show you how we do it, but then we will discuss that later in math. So cross product or vector product of vectors. Okay, so let me draw two vectors in the XY plane, and then we are going to generalize that to 3D, like we usually do, because it's easier to show it in a 2D word. I'm going to draw two vectors. I'm going to call the first one, like we did with the dot product. I'm going to call the first one, let's say V1 or A, just A. That makes an angle of alpha with the horizontal. And the other one would be B. That makes an angle of beta with the horizontal. Now, let's write the definition of the cross product first, and then we are going to derive it so that you understand where these numbers or these come from. We are going to write A cross B. Remember, on the other side, we said A dot B. So when we use cross, it's enough for us. We don't have to say, oh, this is not the dot product, this is the cross product. I'm using a cross. If one of your parents or grandparents was an engineer and has engineering books, you may see the X here written as a caret. It's the same thing. The only time is that in the old days when we printed books, I wouldn't differentiate between an X and a times, and it was not easy to differentiate, and it would be a source of confusion. That's why people used a caret. So they would say A caret B. So we know it's a cross product, not times B. I'm multiplying two numbers, so to speak. Okay, nowadays there is no confusion. We can use boldface and different prints. So we know we are talking about cross product. And this would be the magnitude. I don't have to say the magnitude of A. Well, we can. So let's do it. It's the magnitude of A times the magnitude of B. Remember there? We said cosine theta, where theta was the angle between the two vectors. Here we say sine theta. And now somebody would say, what? But that's it. That's a number, that's a number, that's a number, so that's a scalar. And you said it's a cross or vector product of vectors. So how come you make the scalar vector? Yeah, we are going to multiply it by a unit vector normal. So n here means normal. This E sub n is a unit vector, meaning a vector of magnitude 1. So the magnitude stays AB sine theta, unit vector, perpendicular to both A and B, meaning perpendicular to the plane of A and B, right? If you are uh, perpendicular to two vectors, means you are perpendicular to the plane. So A and B here are in the plane of this paper, which is the XY. So the cross product of A cross B or B cross A would be perpendicular to the XY plane, meaning it's parallel to the Z. But is it up or is it down? Because now it's a vector. The direction is extremely important, or the sense of the vector being going up or down. We follow the right-hand rule. Following the right-hand rule. What does that mean? Remember we said they tell you to use your fingers, and I said it's easier to use a screwdriver or just a bottle cap. So if I have a bottle here in the XY plane where the two vectors meet, and I turn it from X to Y, because, or from B to A, like that, it will move up. So B cross A would be a positive K. It will have a sense of positive direction parallel to the Z axis. But if I say A cross B, I'm turning clockwise, so the bottle cap will go down. It's negative Z. Huh. So now I can say that A cross B equals negative B cross A. That's important. It's not like the dot product that can move things around. No, here it's very important to understand which is which comes first. Not only that, we know that A cross A is the magnitude of A, which is 1, times the magnitude of B, which is 1, times the sine between A and itself. But the angle between A and itself is 0, and sine 0 is 0, so that equals 0. But if you have two, so in the dot product, if two vectors were perpendicular to each other, the dot product is 0. Here, if I have I cross J, so let's write those. So first of all, we can say I cross I equals J cross J equals K cross K. Magnitude of each is 1, but the sine between them, the angle between them is 0, and sine 0 is 0, so all of these equal 0. But then if I say I cross J, I is the X, J is the Y. So if I'm going from X to Y, that's moving up. So it's positive K, which means J cross I equals negative K. And likewise, if I say J cross K equals I, and K cross J equals negative I. And finally, K cross I equals J, and I cross K equals negative j. And somebody will say, oh my God, do we have to memorize these, which is positive, which is negative? I say, well, some people made it easy for you to draw a circle and write I, J, K in a clockwise manner. If you are following the arrows, you get positive. If you go back opposite to the arrows, you get negative. What do you mean? I mean I cross j is k. I cross j is k. J cross k is I. J cross k is I. K cross I is j. K cross I is j. But if I'm going in the opposite direction, I say j cross I is negative k. Yeah, j cross I is negative k. I cross k is negative j. I cross k is negative j. K cross j is negative I. K cross j is negative I. So that's a quick way to remember. And as you will see later, you really don't need to remember that. We'll see how it works. So let's do like we did with the dot product. I'm going to represent A. Let's make an arrow here. I'm going to write A equals A cosine alpha I plus A sine alpha j. And B would be B cosine beta I plus B sine beta j. And now I'm going to multiply them A cross B. And we do that exactly like we multiply like algebraic multiplication. So A cross B. I have four things. So if I start with the bottom, I say this times that, I can write it AB cosine alpha cosine beta. And then I have I cross I. Notice these are numbers, but these are vectors, so I have to write them I cross I. And then I multiply this by that, so I get AB sine alpha cosine beta, sine alpha cosine beta, I cross j. Notice I started from the bottom, so I multiply this by that, this by that. So I cross j. And then I'm going to move this times that. So I get AB again, cosine alpha, sine beta, j cross I. And finally, I get plus AB sine alpha, sine beta. Notice I multiply from bottom, so j cross j, it doesn't matter because they are both j. We know that I cross I and j cross j are zeros. So this is 0, this is 0. We also know that I cross j is k, but j cross I is negative k. So now I can say AB times sine alpha cosine beta, that's k, and this is negative k, so minus cosine alpha sine beta k. For those of you who remember how to simplify that, sine cosine minus cosine sine is sine alpha minus beta, so equals AB times sine alpha cosine, I'm sorry, sine alpha minus beta k. But alpha minus beta is the angle between them, which we refer to here as theta. So it's AB sine theta k. Magnitude of A times the magnitude of B times sine theta times a unit vector k perpendicular to both. Notice I started from the bottom. I say this times that, this times that. So what we did really was B cross A. If we had done A cross B, all of these would get backwards and we will get negative AB sine theta k. So it would be going down. Again, I'm sorry, I wrote A cross B, but I did it B cross A because I wanted to show you, I wanted to end up with a positive and I didn't realize I already wrote A cross B. If I start from top, it would be cosine alpha sine beta, and then sine alpha sine beta would be negative, sine alpha cosine beta would be negative. So these two would change signs, and I will get a negative outside if it's A cross B. Some people would say it's still too confusing. Yeah, it is, because I was just trying to show you how did we come up with this equation to derive it for you. But in reality, we are not going to do any of that. It's just was. So let's take two examples. I'm going to give you an example in 2D and an example in 3D and see how we are going to do it. Okay. So suppose I have vector A is in 2D, let's say 2i minus 4j, and B is 3i plus j. And I want to find A cross B. So the way we are going to do that is to use a determinant. We draw the determinant like that, okay? Two lines without, not two brackets like we did with matrices. For lack of terminology, well, let's see how we do it first, and then we can discuss. We start the first row by writing I, j, k, which are the three unit vectors of our coordinate systems. I want to do A cross B, so A comes first, then B. If I wanted B cross A, I would enter the coordinates, so B first, then A. Okay? So I have a 2 for the I, negative 4 for the J, and 0 for the K. And then I get 3, 1, 0. And then we try to find that. How do we find the determinant of a 3 by 3 matrix? So that was originally a matrix, and I wanted to get its determinant. A method that we will be using in this course, because it's pretty much the easiest method, and it only works for a 3 by 3 matrix. It doesn't work if you have a 4 by 4, okay? So the way we are going to do it is, or this method is called the augmented column method. We rewrite the I and the J only. The I and the J, 2, 3, negative 4, 1. And then we say, okay, so the determinant here, which would be A cross B, equals. I'm going to open a bracket, and inside the bracket, just to be in the beginning, I want you to get used to it and don't get distracted with positives and negatives, so I will make it easy for you. Open a pair of parentheses here and a pair of parentheses there with the negative sign in between, so that you will never get it wrong. We are going to multiply the elements along the main diagonal. I times negative 4 times 0, it's 0. Plus j times 0 times 3, another 0. And then for the k, I'm going to multiply k times 2 times 1 is positive 2k, so I write positive 2k. And then I'm going to start with the other diagonal. K times negative 4 times 3 is negative 12k. So let's write negative 12k at the end, since we write the I and the j. I times 0 times anything is 0. And j times 2 times 0 is also 0. So at the end of the day, I get 2k minus negative 12k equals 14k is the moment. Or I'm sorry, is the cross product. We'll talk about moments next time. But that's how we calculate the moment. So 14K is the answer. Yeah, both are in the IJ plane, so in XY plane. So this guy has to be in the Z. And why is it positive? Because if you draw these, 2I minus 4J looks something like that, right? And 3I plus J looks something like that. So this is A, and this is B. And if you rotate from A to B, you are opening the bottle cap and it's moving towards the positive Z. That's why. If you had done B cross A, you will get this. This would be negative and this would be negative, and you get negative 14K. The exact magnitude, of course, but opposite sense. Finally, so that I don't make it too long for you, we are going to take two vectors in 3D. So let's say A equals 2I minus 3J plus 5K, and B equals negative I plus 4J minus 2K. Anything, just any three numbers. So let's say how we find A cross B. We are going to have the determinant I, J, K, I, J. Notice we replicate the first two columns. 2, negative 3, 5, 2, negative 3, 5, 2, negative 3. And then negative 1, 4, negative 2, negative 1, 4, negative 2, negative 1, 4. And then I'm going to say equals. I'm going to open pair of parentheses minus another pair of parentheses. We'll go along the I. Negative 3 times negative 2 is positive 6, so I get 6I. 5 times negative 1 is negative 5J, so negative 5J. 4 times 2 is 8, so positive 8K. And then I'm going to go in the opposite. We prefer to start with the I, IJ, and then we go back to the K at the end. So I get 20I, negative 4J, plus 3K. So 6 minus 20 is negative 14I. Negative 5 plus 4 is negative J. And 8 minus 3 is positive 5K. And again, we found the cross product very easily using this method. I hope this was clear. And that's how we are going to find the magnitude and the direction of vectors, which would be the moments or the torques, as you may have used in physics, the magnitude of the torque and its direction. And then later we will see, okay, so how do I keep a body where all the forces are not concurrent, how to keep it, constrain it so that it doesn't move in any direction and it doesn't rotate in any direction. We'll start with the 2D rigid body equilibrium and then go to the most complicated thing we will cover during that period of the course, which is the 3D rigid body equilibrium. It's pretty straightforward. If you know these basics, how to find the dot product and the cross product, everything after that should be fine. I hope this was an easy session for you, and I hope to see you soon. Thanks and have a nice day.